Hello everybody and welcome back to another Engsci recap video. Today I'll be talking about the course MA292 Ordinary Differential Equations. My name is Jason. I'm going into my third year of engineering science in fall of 2022 and I'll be majoring in the biomedical systems engineering option. So what is MAT292? It was a course I took last year in my fall term, and the instructors at the time were Professor Vardan Papyan and Professor Fabian Parsch. The main course topics were uh, very focused around differential equations, as the name of the course would suggest. So we began with general modeling with differential equations, and then we talk about more analytical techniques like phase lines, direction fields, and phase portraits, as well as equilibria, the method of integrating factors, which is a method of solving differential equations or specific kinds, existence and uniqueness theorems, systems of two first-order ODEs was a big part of this course. And in fact, I will be covering a question in this video that was testing this concept. We also talked about numerical methods and error, specifically with respect to Euler's method and more advanced numerical methods like the Runge-Kutta. We also talked about general first-order linear systems, as well as the matrix exponential, second-order linear equations, the Laplace transform, as well as Heaviside and Dirac delta functions, and the Fourier transform. So the question I'll be covering in today's video is from the term test that I wrote on November 1st, 2021, and this is question 10. So this question covers topics including Newton's law of cooling, which is an example, of the kind of modeling that we would do using differential equations. And it primarily tests systems of two first-order ODEs, and specifically the zero eigenvalue case. And you will see what I mean when I solve this problem. But this is the problem in its entirety. And the questions pertaining to this problem will be on the next slide. So consider the temperature of two adjacent rooms in a house. We'll denote by A of t the temperature in room A and B of t the temperature in room B. We measure temperature in degrees Celsius and time in hours, so those are just our units. There are two effects coming from the fact that the air in one room heats or cools the air in the other room. So number one, the temperature in room A changes at a rate proportional to the difference in temperature between room A and room B. The proportionality constant is 2. The temperature in room B changes at a rate proportional to the difference in temperature between room B and room A, and the proportionality constant is 3. So here are the questions. So part A, find two ordinary differential equations involving A of t and B of t and explain. Part B, the ODEs that you found in the previous part produce a system of two ODEs. Find the coefficient matrix. Part C, explain from a physical perspective why it's impossible for the matrix in part B to have positive eigenvalues. Part D, find the general solution to the system and draw a labeled phase portrait. And part E, find the equilibrium or equilibria of the system and explain the result from a physical perspective. So part A, we'll first set up the ODEs. So we are given this bit of information in the question, that the temperature in room A changes at a rate proportional to the difference in temperature between room A and room B with a proportionality constant of 2. So mathematically, we can denote this by saying A prime is equal to minus 2 times A minus B. And we know that our signs are correct because let's say A is greater than B. And remember, A and B are temperatures, which are functions of time. If A is greater than B, then that means A should be decreasing. And from a physical standpoint, this makes sense. The hotter room will lose thermal energy and it'll decrease in temperature, whereas the colder room will get warmer. We can apply the same logic to get an equation for B prime. but this time we'll note that we need to flip the position of A and B so that B prime is equal to minus 3 times B minus A. And this is because we note that if B is greater than A, then B will be decreasing. And the reason this is true is because B is decreasing when B prime is negative, and if B is greater than A in this equation, then we see that B prime should be negative and should be decreasing. So now that we have our system of two equations, we can construct our coefficient matrix as part B asks for. So these are our two equations as summarized from the last slide. And so we can just put this simply into a matrix format. Again, we just use coefficients to denote the coefficients in front of A of t and B of t. And we'll note that this 2 and this 3, they come from the fact that when you expand out these right-hand sides of the equations, you will get a positive 2 and a positive 3 in our system. So that is what the coefficient matrix looks like. We can check. We can say A prime of t is equal to minus 2 A of t plus 2 B of t, which corresponds to our first equation, and B prime of t is equal to 3 A of t minus 3 B of t, which corresponds to this second equation. So that is indeed correct. So now to answer part C, we need to think about this from a physical perspective, and the question asks us why it's impossible for there to be a positive eigenvalue. So when we solve these kinds of systems where we have two linear equations, then if the matrix has a positive eigenvalue, call it lambda, then that means for certain initial conditions, at least one of A of t and B of t will have a term c times e to the lambda t, where c is an arbitrary constant. And this is just from understanding the rules or the different cases that you have to consider when you're solving these two equation systems. This is simply a fact. If there is a positive eigenvalue, then we will have this term c times e to the lambda t in one of our equations. The problem with this is that, as you can see, when t goes to infinity, this term will diverge either to infinity or minus infinity, depending on the sign of c. This means that either A of t and or B of t will diverge to infinite temperature, which doesn't make any sense physically. This is not really possible because we have just a system of two rooms and there is no heat source or heat sink, so there's no reason there should be any form of infinite temperature. So this is why, before we even solve our coefficient matrix, that there cannot be a positive eigenvalue. So now for part D, we want to actually solve for the general solution, and we want to draw the phase portrait. So first of all, we need to find the eigenvalues of the coefficient matrix. Here I've called it M. And in order to find the eigenvalues, we will take the determinant of M minus lambda times I, where I is the identity matrix, and lambda is just our eigenvalue, which we do not know yet. So the determinant is equal to this expression, and we set that equal to 0. So we get lambda squared plus 5 lambda is equal to 0. Solving this, we get two possible eigenvalues, 0 and minus 5. And now for each of the eigenvalues, we can find the corresponding eigenvector. So we can set this up by taking M minus lambda 1 multiplied by the identity matrix, and we multiply this by V1, which corresponds to the eigenvector for lambda 1, and this should be equal to the 0 vector. Again, lambda 1 was just 0, so M minus lambda 1I is simply M, and V1, since we don't know V1 yet, we'll just call its entries A and B. So now we get a system of two equations, and we can find that A is equal to B in this case, note that these two equations aren't linearly independent. So, and this makes sense because V1, we don't actually care about the specific values of the entries. We just care about the relationship between A and B. So in this case, we can write V1 as the vector 1, 1, but we could also have written it as 2, 2 or 3, 3 because there is an arbitrary constant in front of it. As for V2, we do the same solution method, but instead we replace lambda 2 with -5 because that was the second eigenvalue. And we see that, again, we only have one linearly independent equation relating A and B. So we get that A is equal to -2/3 B. So we can write our vector V2 as -2, 3. Again, there is an arbitrary constant in front, but I've left it out for simplicity. So now we can construct our general solution. Just to recap, to remind all of you, when we are solving these kinds of two equation systems, our general solution will look like this. So A of t and B of t in vector form will have a solution containing the eigenvalues of the coefficient matrix and the eigenvectors. Now that we know all of our eigenvalues and eigenvectors, we can simply plug them in. Notice how the exponential term in the first term goes to 1 because lambda 1 was simply 0. V1 is the vector 1, 1. Again, lambda 2 was -5, and V2 was the vector -2 and 3. And recall how when we were solving for the eigenvectors, we had general coefficients in front, but those can simply combine with the general coefficients C1 and C2. So we don't actually have to care about them. And so now this is what our phase portrait looks like. So our phase portrait will be drawn according to what eigen vectors we have and their corresponding eigenvalues. So V1 is simply a line. Because its value is 1, 1, this shows the line where A of t is equal to B of t. And V2 corresponds to the vector -2, 3, which essentially shows that there is, because the entries are negative of each other, as B increases, A will decrease and vice versa. And because the eigenvalue corresponding to this eigenvector is also negative, these directions will be pointed towards this central line, this red line, which corresponds to the eigenvalue of 0. And this line, the red line, doesn't have any direction to it because the eigenvalue is 0, which means that when the values of A of t and B of t approach this line, it will essentially stop changing. And that represents our equilibrium, which I'll discuss on the next slide. So again, as we noticed from our phase portrait, there is an equilibrium line at A of t is equal to B of t. The reason for this is when A of t is equal to B of t, we find that A prime of t is 0 and B prime of t is also equal to 0. And from a physical perspective, this makes sense because if there's no temperature difference between the two rooms, then there's no heat exchange. And again, the rate of heat exchange is corresponding to A prime of t and B prime of t, and the physical temperature would be A of t and B of t. So that is the solution to that question. And before I end off this video, I'd like to make some quick acknowledgements. I'd like to thank Professor Papyan and Professor Parsch for the course and term test content. I'd also like to thank my two TAs from this class, my tutorial TA Thomas and my MATLAB TA Adrian, as well as the individuals who this Beamer template is inspired from. So thank you so much, and I'll see you in the next video.